Hi everyone, and welcome to my virtual talk at WINE 2020. I'm going to be talking about the paper Almost Envy-Free Repeated Matching in Two-Sided Markets, and this is joint work with Kostas Kolias and Srinivas Golapudi. What are two-sided markets? Well, first we have to understand one-sided markets. In the traditional one-sided market paradigm, there's a supplier who will create the object of value and send that to the company. The company then distributes and sells that to the customer, who pays some revenue to the company. The company then sends some of that revenue onto the supplier. The customer will have preferences over different products, and they can choose which to buy. In contrast, the supplier and company don't really care about which customers they get, they just want the revenue. So we can think of the customers not really providing value to the supplier or the company outside of the revenue. In contrast, in two-sided markets, both sides of the market are actually providing and receiving value. And we can also think of this as both sides of the markets having preferences over the other side. There are lots of examples of this. So for example, drivers and riders on Uber or Lyft. So in this case, the drivers are providing some value in the form of the ride, but they also have preferences over different riders. Maybe some routes will take them on bad roads, or some routes will consume more gas, or some riders are unruly and unpleasant to be around. We also have Airbnb, which matches travelers with hosts. Upwork matches employers with employees, and there are a lot more. And in all of these cases, both sides have preferences over the other. In some cases, one side is providing revenue and the other side is getting revenue. So for example, the riders are paying money and the drivers are getting paid. But in other cases, it might not be as clear. Fairness in two-sided markets is very important. And there are lots of papers academically and also just journal articles in the popular media that have talked about this. And the Uber drivers have a boss, the algorithm, working with machines, the impact of algorithmic and data-driven management on human workers. And part of the reason for this is that there's a huge power dynamic between the users and the platform. So as the Uber drivers have a boss, the algorithm headline alludes to, we have all these riders and drivers who are using the platform, but the platform's algorithm gets to make a huge amount of decisions that can have huge impacts. And while we don't think that these algorithms are intentionally malicious, we also want to make sure that they're actively fair to the users. Okay, so our model is going to involve two sets of agents, N and M. We're going to assume that they're the same size. We'll look at an infinite time horizon. On each time step, everybody's going to get one match. So we'll choose a perfect matcher between N and M. Okay, and it can be different matchings on different time steps. The idea is that the cumulative matching should be fair after every time step. Okay, and we're going to work with additive evaluations. What does fairness mean? Well, there are a lot of different notions of fairness. One of the most common is envy-freeness, and that states that no agent prefers another agent's set of matches to her own. So this is a very common property for one-sided preferences, and it's not always possible for indivisible resources. For example, if there are two drivers that both want a single rider, the rider is only going to go to one of them and the other one is going to be sad. A relaxation of this that's also very common for one-sided preferences is called envy-freeness up to one good, or in our case, envy-freeness up to one match. And this says that it's okay if I envy you, but there should be a match that you've gotten that if we remove that, I would no longer envy you. And this is called EF1. This is very common for one-sided preferences. And in this paper, we want the cumulative matching to be EF1 after every time step. So the idea is that if we have these two drivers and one rider, on the first time step, one of the drivers is going to be unhappy, but on the second time step, they'll get a rider that they're happy with. And even though they're unhappy on the first time step, if we removed that rider, there would be no envy. So this is EF1. However, even EF1 turns out to be quite hard in this two-sided setting. So we'll focus on binary valuations, where each match is either good or bad. And this is a strong assumption. I think it's somewhat can be justified in terms of elicitation. It's hard to ask, a rider, what is your value out of 10 for this driver? It's a lot easier to say, do you feel like this is a good match or a bad match? So when valuations change over time, even for binary valuations, EF1 is impossible. And we can see that through this simple example. These arrows are representing which agents like which other agents. So in this case, agent 1 thinks agent 2 is a good match, agent 2 thinks agent 3 is a good match, and so on. So you'll notice this is a cycle, and it's asymmetric in that every agent likes an agent that doesn't like them back. So what happens? Without loss of generality, suppose on the first time step we choose this matching. So agents 1 and 3 are going to be happy, but agent 2 is going to envy agent 4 because 4 was matched to 3, which 2 likes, and 4 will envy 2 because 2 was matched to 1, which 4 likes. On the next time step, suppose that this is the new valuation. So the valuations have changed, and now agents 2 and agent 4 both want agent 1. One of them is going to have to be matched to agent 1, and that one will be happy, but the other one is now going to envy that one even more. So agent 4 already envied agent 2, but now that envy has increased and EF1 will be violated. And what this shows is that for binary valuations, when valuations change over time, you can end up with these envy cycles that are really difficult. And in the one-sided paradigm, there is a very common strategy for getting rid of the envy cycles, which is you can just permute the agents bundles along the cycle. That actually doesn't work here because it's going to affect all the bundles on the other side of the bucket too. So it's a little trickier. And we are sad. So what if evaluations don't change over time? Well, if you want some sort of efficiency, and our notion of efficiency is going to be that you choose a maximum weight matching on every time step. So if you want that, it's still impossible. And the example for that is a little more complicated, so I'm not going to show it now, but it's in the paper, of course. What if you don't care about efficiency? So you just want EF1, binary valuations can't change over time, and you don't care about efficiency. That's our main open question. Okay, so how can we actually get a positive result? Symmetry to the rescue. Valuations are symmetric if Vi of j is equal to Vj of I. So if agent I likes agent J also likes agent I. For binary valuations, this means that either Vi of j and Vj of I are both equal to A, where A is some constant, or they're both equal to 1. And the motivation here is that if maybe I'm a rider and I like drivers that are close to me. If I'm a driver, I probably also like riders that are close to me so I don't have to drive too far. Maybe on Upwork, I would like to be matched to some particular employer because I think we're a good fit, and hopefully the employer also thinks we're a good fit. In real life, I do want to recognize that this is a strong assumption. I argued in the previous slide that at least to some extent it's necessary, but it certainly is a strong assumption. So let's again consider the instance we looked at before, where on the first time step, there is this cycle. Suppose we do that same matching of of 1 and 2 get matched and 3 and 4 get matched. And that would have created an envy cycle like we talked about before. But now, if valuations are symmetric, that means that agents 2 and 4 are also happy, so there's no envy. Okay, so the crucial thing going forward is going to be preventing envy cycles. And this is the main lemma. If valuations are symmetric and binary, let's assume there are no envy cycles at time t and that we choose a maximum weight matching at that time. Then there are no envy cycles at time t plus 1. And I'll show some intuition for this. So let's imagine that at time t plus 1, there is an envy cycle. And let's suppose 2 envies 4 and 4 envies 2. Well, one of these edges is new because there was no envy cycle at time t. So let's assume that 4 just started envying 2. 4 didn't used to envy 2. Okay. What that means is that agent 4 likes agent 2's match, but not her own. Because if agent 4 liked both of their matches, if 4 didn't envy 2 before, so she would still not envy 2. This means that agent 4 has to like agent 2's match, but not her own. It also means that agent 2 likes agent 4's match at least as much as her own. Because agent 2 might have already envied agent 4, but if agent 2 got a match that she liked more than agent 4's match, that envy would actually go away. That's not immediately implied by everything I've said so far. You have to pay attention to also the magnitude of the envy. Okay? So what you can actually do is just swap their matches. After the swap, agent 4 is now going to be happy because she's getting a match she likes, and agent 2 is going to be at least as happy as she was before. Agent 1 is also happy because of symmetry, and this is the crucial use of symmetry. After we swap, the new agent getting matched to agent 4 should still be happy, and agents 2 and 3 can't be less happy like we talked about. This implies that the new matching has higher weight, so the previous one was not a maximum weight matching. And this is essentially how you can use symmetry of valuations to break the envy cycles. And this was just for a 2 cycle, but if you have a longer envy cycle, you can permute the matches along the cycle. The proof is a little more complicated, but it does work out. So with that in mind, I'm going to show the algorithm. It's actually quite simple. We start with a cumulative matching capital X, which is empty. On each time step, create a maximum weight matching given the current valuations. And we look at what would the new cumulative matching be if we used little xt. If it's not EF1, find a pair of agents that violate that and swap their matches. And this will actually work out. So it's not immediately obvious, but if you keep doing this, the envy cycles will actually go away. It's trivially EF1 after each time step, and that's all assuming the while loop terminates. Like I said, the key property is no envy cycles. The way we show that is that each swap is going to move an edge up in the envy DAG, and we know it's a DAG because there were no envy cycles coming into it. This means there can be at most O of n squared swaps, and then the crucial thing I mentioned before is that there will still be no envy cycles on the next time step. Also, we mentioned that we start with a maximum weight matching, but after all these swaps, we need to show that we still end with one. It's not super hard to do, but I'm not going to do it in this talk. It requires a little bit of work. Okay, so the main result is with this algorithm, if we assume that valuations are binary and symmetric, and we do allow them to change over time, so valuations can change arbitrarily between time steps, then the matching is going to be EF1, and a maximum weight matching is chosen on every step. And like I said, the result holds even for dynamic valuations, so valuations that change over time. So even though these are strong assumptions, we're saying that we can have a strong fairness guarantee for every time step, and we can also have an efficient algorithm, and that's choosing the maximum weight matching on every time step. Recall that, as we talked about before, for binary but not symmetric valuations, the first two are impossible, and 1 and 3 are also impossible. Okay, so to wrap up, two-sided markets create a huge power dynamic between the platform and the individuals. Fairness is crucial. We propose the model of envy-freeness in this two-sided repeated matching setting, with envy-freeness and EF1 being widely studied properties for the one-sided preference setting. For binary and symmetric valuations, we were able to give an algorithm that produces a cumulative matching, which is EF1 after every time step, and chooses a maximum weight matching on every time step, and holds even for dynamic valuations. Without symmetry, the first two and 1 and 3 were impossible. So what about just 1? This I mentioned before. What if you're okay with binary valuations, but you don't want to assume symmetry and you don't care about efficiency? That's our main open question. So going forward, I think it would be interesting to look at two-sided preferences in other contexts also. This was in this repeated matching setting, but what about in a more static fair division setting? What about in other types of settings? One-sided preferences have been widely studied, but two-sided preferences not as much. Another kind of different direction for future work is we had some quite strong counterexamples, and we had to make some strong assumptions in order to get a positive result. Maybe that indicates that this isn't quite the right model. Maybe there's a better way to frame it, and that we'll be able to get also a positive result without having to make quite as strong assumptions. So I think that's worth investigating as well. Okay, and that's all I have. Thanks for coming to my talk.